Good day, everyone. So we're reviewing Wetzel's Limnology textbook. This is edition number 4, and we're on chapter 14, the nitrogen cycle. And today we'll be tackling the nitrogen budgets in lakes and reservoirs. The discussion of nitrogen sources, transformation, and fate in lakes and reservoirs in the sections above highlights the complexity of the nitrogen cycle. The use of nitrogen budgets for lakes and reservoirs provides a way of simplifying this. Typically, nitrogen loading has been shown to be an excellent predictor of nitrogen retention in lakes and wetlands in a study of 23 wetlands and lakes in North America and Europe. Wetlands can retain twice as much nitrogen as lakes, and denitrification was the primary mechanism for nitrogen retention. Groundwater inputs of nitrogen are not well studied, in part because the methodology is challenging and it is difficult to get accurate estimations, particularly for whole system nitrogen budgets. Groundwater often has high concentration of dissolved inorganic nitrogen, particularly nitrate. Nitrate that has seeped into the shallower depth of the sediment of lakes and reservoirs, where there may be a redox potential created by settling organic matter, may be rapidly denitrified. A global study of lakes and reservoirs found that these water bodies played a major role as sinks for nitrogen, retaining 19.7 teragram of nitrogen per year globally. Small lakes were responsible for almost half of this global retention. The degree of retention was shown to be a function of climate and the density of lakes and reservoirs across the landscape. Reservoirs play a greater role in nitrogen retention than lakes due to a combination of higher drainage ratios, catchment surface area to lake or reservoir surface area, higher apparent settling velocity for nitrogen, and greater average nitrogen loading rates in reservoirs compared to lakes. Maringer et al. Showed that 6% of global inputs of nitrogen to freshwater was processed by reservoirs as either denitrification or burial. So figure 14-6, so this is ANAMOX, estimates across a variety of aquatic ecosystems globally. The bars represent the range of total nitrogen or dinitrogen production that can be attributed to ANAMOX in a given study site. Purple bars designate marine and brackish ecosystems. Blue bars designate freshwaters. The Thames River, estuary, and the coastal wetlands, China, are hatched because the study spanned a range of freshwater and marine influence sites. So let's see here. First, I think we're talking about this hatched area, even though it's not really hatched. So this is the Thames River, and this is the Chinese coastal wetlands. And on the y-axis, we have the percentage of nitrogen from ANAMOX. And on the x-axis, we have specific watersheds. And so therefore, we have ranges with these bar graphs. So we have very large ranges, for example, for this, for US and Sweden coastal sediments right here. We also have pretty high values for Denmark estuary sediments. And they were saying blue bar designate freshwater. So we're dealing with freshwaters here. And we don't have as much variability compared to the brackish or saltwater environments. And then some of them start pretty high already. So where the percentage of nitrogen, of dinitrogen, is attributable to ANAMOX. For example, for this lake here, which is North American Lake Superior, and then the German lake in Rasnitzer. And then we have some, actually, where we have very small amount of ranges, like China, paddy soils. So paddy soils, I think those are like rice field-based soils. And then here, and then, for both the Thames rivers and the Chinese coastal wetlands, we have small values attributable to dinitrogen from NMOX, up to like about 10%, 10, 12%. All right, so most nitrogen budgets have been constructed for temperate areas of Europe and North America, where seasonal effects may be more pronounced than in tropical and subtropical areas. One study of semi-arid lakes in Australia found that only 7% of nitrogen in lakes was retained, a percentage that is lower than in lakes in the United States. Despite nitrogen fixation inputs in this study, it was counteracted by similar rates of nitrogen burial in the sediment. The contribution of denitrification was highly uncertain, as estimates were based on measured relationships between nitrogen loading and denitrification rates in temperate regions. So this is another map. Let's see. So this is figure 14-7. So the NIRELA model global distribution of percent nitrogen removal by lakes and reservoirs, and B, nitrogen removal by lakes and reservoirs in kilogram of nitrogen per kilometer square per year. So the first one is the amount of nitrogen retained, and then the second one is the amount of nitrogen removed. And so this is all in percentage. And so therefore the red areas, all the nitrogen is retained, where in the white areas, no nitrogen is retained. And that would make sense. Like, for example, the Sahara Desert, some of the desertic areas, we don't have much nitrogen that is getting retained, because probably we don't have a lot of precipitation in those areas. Or the denitrification rate is higher than the amount of the process that would drive the nitrogen burial. Then we have the agricultural region of the Midwest of the United States. We have a fair amount of nitrogen retained, although it's not super high. I mean, we can see like it's in the 11.5 up, maybe up to like maybe like about 75% that is retained. So therefore, there's a fair amount of effluent here that has nitrogen in it. And what other patterns can we derive from this? The equatorial region looks like there's not much that is retained. So most of the nitrogen is actually quickly cycled into the plants and or removed through denitrification. Speaking of that, let's look at the total nitrogen removal rate. And so in nitrogen poor areas, for example, we have very low amount of nitrogen being removed in the Arctic regions of the world here, as well as some of the desertic region of the world. And we have very high removal rates in the Great Lakes region, in southern Sweden, southern Finland, in western Russia, right here, St. Petersburg area. And then in terms of removal rates, very low. Besides the Arctic region, we also have the equatorial region and some of the desertic region, although at the same time, we also have like removal rates of about 0 here in the desertic region, like in Australia and Sahara, and then the Horn of Africa, the Arabian Peninsula here. And of course, Greenland, we don't have any removal rate. I mean, it's mostly ice, so there's not much nitrogen that is reaching the soil just yet. Okay, let's see. So most nitrogen budgets have been constructed for temperate areas of Europe and North America, where seasonal effect may be more pronounced than in tropical and subtropical areas. So we already went through that. So let's move on to subchapter 3, nitrogen sources, transformation, and fate in streams and rivers. Nutrients move unidirectionally within lotic systems, streams, and rivers, and as such have some different characteristics in terms of nitrogen cycling compared with lakes and reservoirs. Dissolved substances move downstream, where they may be bound or assimilated for a period of time and later released for further movement downstream. Hydrological processes physically move water containing dissolved and particulate components to reactive sites. Exchange of reactive sites include chemical ionic transformation, absorption and desorption, and metabolically mediated uptake and assimilation by biota. Materials can be transferred from the water column to the stationary stream bed. Some of these materials will be retained permanently removed from the system via gaseous form utilized by incorporation into living organisms, potentially transferred to other organisms, and subsequently released by animal excretion or decomposition to the water column, and further transported downstream. As the nitrogen cycles among biota and abiotic components of the stream ecosystem, they are transported downstream in processes that resemble spirals and have been termed nutrient spiraling. Although upstream movements of nutrients can occur in backflows from eddies, fish migration, and flight of adult aquatic insects, net fluxes are downstreams. So before we move on to that section, let's look at this figure here. An approximate, so this is figure 14-8, an approximate budget of nitrogen and phosphorus in the lower lakes at the terminus of the Murray River in Australia, spanning the years of 1979 through 1996. Quantities shown are the average annual rates normalized to the surface area of the lake over the 17-year study period, with units in millimoles per meter square per year. Total nitrogen denotes total nitrogen. TN. TP denotes total phosphorus. FRP denotes filterable reactive phosphorus. TKN denotes total kjetol nitrogen, the total concentration of organic nitrogen and ammonium. DEN denotes denitrification, and N-fix denotes nitrogen fixation. So one is the opposite of the other. The denitrification is the loss of nitrogen to the atmosphere, and nitrogen fixation is actually the gain of nitrogen to the soil or to the plant. So we have like a system here, which is the lower lakes, and then we have the inputs and the outputs. So the inputs, we have atmospheric deposition, and we have 26, and that would be in millimoles per meter square per year. River imports, and we have 690, so it's very large contribution. Nitrogen export, we have 670. Nitrogen burial, we have 620. And so therefore, if we looked at the total nitrogen in here, we have 20 in terms of being retained, so 20 plus 26 at about 46. 46 plus, let's say, this is a range, so 46, let's say, for 650, so we have about 700, and so therefore we have 620 in terms of burial, so we may have like about 80 millimoles of nitrogen per meter square per year staying in the lake, something to that effect, although I didn't count this one, maybe about 10, something to that effect. So it's not really a very strong eutrophic lake. Surface exchanges. So this is solute processes in lakes, in streams. The two spirals represent the continuous exchange. So this is spiral number 1, number 2. The continuous exchange of solutes and particle-bound chemical substances between the water column and the stream bed, and between the stream bed and interstitial water. Material in the water columns and interstitial water are moving downstream, while the stream bed material are stationary. So let's see. So this is like surface exchanges in blue. We have rainfall, surface runoff, littoral fall, blow-in, bank and floodplain erosion, floodplain deposition. So then we have some gain and some loss here, egg laying, gas exchange, it goes both ways. And then, so this is the water column, and we have solutes, so this is how nitrogen will move, and this is a transport mechanism. And then some of that solute, some of the nitrogen gets absorbed. The microbes may uptake it, precipitation, complexation may have some portion of it. and then some suspended particle and microbial organism lost to solutes, so desorption, leaching, mineralization, and dissolution. And so they were talking about the fact that we have two spirals here. So we have spiral number one, and then we have spiral number two. And what they are supposed to symbolize is the continuous exchange of solute and particle-bound chemical substances between the water column and the stream bed, and between the stream bed and interstitial water. So this is between the water column and the stream bed, right here, and this is between the stream bed and the interstitial water. So that would be the water that would be found within the stream bed, within the sediment, in the pore space of the sediment. So stream bed, we have expansion, we have desorption, dissolution, and that is contributing to this spiral, and so therefore to this gain into the water column. And then we have plant uptake, and so that's a loss. And so exudation, sloughing, although that's a gain. And then we have also the same process, at least sloughing that may contribute to interstitial water. Then we have consumption, so we have actually some of the interstitial water that is helping biota to flourish. We have adsorption, detritus, and microbial organisms. And then we have leaching, resuspension, desorption, and mineralization here in terms of loss, so both to the water column and to the interstitial water. And then filtering, feeding, consumption, and consumers, excretion, we have that loss to the interstitial water. And so I think that's pretty much it here. Figure 14-10, spiraling in a river ecosystem of two compartments, water W and biota B. So water is W and biota is B. The spiraling length S, right here, the sum of the uptake length SW, so this is the sum of the uptake length, and the turnover length SB. SB is right here. The sum S is equal to the sum of the uptake length. So S is the sum of the uptake length SW, and the turnover length SB. So SB is the turnover length, which is right here, estimated from the downstream nutrient fluxes FW and FA. So FW, FA, and those are exchanges from the river. And then we have a flux of the uptake. So U. So this is the flux right here, and retention. This is the R right here. Spiraling length is the average distance in a nutrient atom downstreams during one cycle through the water and biotic components. The S equals the sum of distance traveled until uptake. Uptake length is SW until regenerate, and the downstream distance traveled within the biota until regeneration, turnover length. The S can be calculated from the downstream nutrient fluxes, mass per unit width of a river per unit time in the water component, FW, and in the biota B component FB, and the exchange fluxes of biotic utilization U of nutrients from the water compartments or regeneration from the biota in mass per unit area per unit time. The average downstream velocity of the nutrient may be near that of the water in large rivers, but is very much slower in streams and rivers where nutrients reside in the sediment and microbiota for a high proportion of the time. The spiraling length of a nutrient suggests the extent of availability and utilization rates. A shorter spiraling length of one nutrient versus another could imply that it is a greater demand and it is possibly limiting the potential growth and productivity of the community. The retention of nutrients for at least some time is necessary in order to maintain ecosystem processes in streams. So the spiraling concept also illuminates stream ecological dynamics. Perhaps a more functional application is to determine the spiraling rates of nutrients among different dissolved, particulate, and animal consumer groups. Such analyses demonstrate the rapid recycling rates and very short spiraling length of the attached microbiota in comparison to abiotic particulate material and consumer metazoan. So I think that's going to be it for today, and tomorrow I'll pick it up with these water flow in streams. And I'll see you tomorrow. Thanks for attending, and talk to you soon. Bye.